My name is Professor Orata, and we are continuing with our lectures in thermodynamics. Today we look at tabulated properties. Tabulated properties. And we are going to look at a very important tabulated property in thermodynamics under what we call steam tables. Steam tables. And our main focus should be on the saturated liquid and saturated vapor. Focus on saturated liquid and saturated vapor. Saturated liquid and saturated vapor. So if you remember, we have the pressure volume curves, that's saturated liquid, that is saturated vapor. Saturated liquid, saturated vapor. So the matrix can be pressure volume. We can also have the temperature entropy matrix. We can have the temperature entropy matrix. Now, if you know the property, a property of, for example, the saturated vapor or saturated liquid, then you are going to be able to tell the other properties which are required to define that particular system. That's very important for us to note. Now, most of these properties, which we refer to as tabulated, they are tabulated in the steam tables. The steam tables. And these steam tables have values for saturated pressure table for steam, a saturated pressure table for steam. There are also values for saturated temperature table for steam. We also have saturated, we also have superheated vapor table for steam, and we also have compressed liquid table for steam. So these are quantities which you are going to get in the steam tables, and they are very important. They are very important. Now, what is the reference, for example, for pressure in the steam table? If you remember, we have talked about, in other lectures, we have talked about phase equilibria. So if you take water, for example, the pressure, temperature profile for water would be, under normal conditions, would be that. So we have solid, we have liquid, and we have gas or vapor. And we say that when on this curve, solid liquid curve, the chemical potentials of the component in the solid and in the liquid is the same. And when you have this particular curve, liquid vapor curve, the chemical potential of that component in the liquid is the same as this chemical potential in the vapor. And if we have the solid gas curve, the chemical potential of that component in the solid is the same as this chemical potential in the gas. And we talked about stability of these phases as being based on the chemical potential. The phase with the least chemical potential is the one which is stable under ambient conditions. Now, we say that there is the variance. If you look at our lectures in phase equilibria, we talked of variance. That's the number of degrees of freedom. So that if, for example, you're in the one single phase region, you can vary both pressure and temperature as you wish, and you don't affect that particular phase. But if you're in the two-phase region where the two phases are coexisting in equilibrium, like liquid and vapor, then in that case, if you choose, for example, pressure, then the temperature is fixed. If you choose temperature, the pressure is fixed. And we said that in this particular point where we have the three phases coexisting in equilibrium is referred to as the triple point. It's referred to as the triple point. And at that particular point, the solid, liquid, and gas phases are coexisting in equilibrium, and the variance of the system, the number of degrees of freedom, is zero. What does that mean? It means that the pressure is fixed. The pressure to the triple point here is fixed, and the temperature is fixed. You have no other choice. So in this particular case for water, it is 0.006112 bars, and the temperature here is 0.0098 degrees centigrade. It is fixed. Now, this is a very important reference point for the steam tables. The reference point for the pressure is 0.006112 bars and that particular temperature. And the other reference point in the steam table is the critical temperature. Which we call TC. And that critical temperature for water that's above that particular temperature, you cannot distinguish between liquid and vapor. That temperature is the critical temperature, and the corresponding pressure is the critical pressure, which we call PC, and in water it is 220 bars. So in your steam table, we have 0.006112 bar up to 220 bars. Now, when you look at the steam table, they will have used different units. Instead of bars, for example, you'll find them in Pascal. So it's very important for you to just note that 1 bar is equals to 10 to the power 5 pascals. So that, for example, if you're talking of the 220 bar, that would be 220 bar over 1 bar times 10 to the power 5 pascals. And then, of course, we want it in kilopascals, so we divide by 1,000. So that would be 220 times 10 to power 2. Remember, we are using that identity of the exponent, where we say that x to the power m is also the same as, we can write x 1 over x to power m as x to power minus m. So that this, I just take it up there, so that I will have now 220 times 10 to the power 5 times 10 to the power minus 3. That becomes 220 times 10 to the power 2, and that, of course, is what? That is 22000 pascals, kilopascals. So that is your reference point. The lowest pressure corresponds to the triple point pressure, and the highest pressure in the steam tables for steam corresponds to the critical temperature. And that critical pressure is 220 bars, which you just convert to pascals, And the other units, that's Newton per meter squared, and so forth. So you need to know some of those. Now, like we have said, once you know a property of whether it's saturated vapor or saturated liquid, then you can get the rest, and actually define completely the state of that system, So suppose the property is X. And we also say that if it is for the saturated liquid, we use the suffix F. Suffix F for saturated liquid. And for saturated vapor, we use the suffix G. G for saturated vapor. So what are we saying? With these properties, we'll get them from the steam table. So let's say these properties, the properties can be anomaly. In fact, the properties are normally enthalpy, which is designated as H, and specific volume, noted as V, internal energy, and entropy. All those are thermodynamic state functions: internal energy, U, and entropy, which is S. I repeat, the thermodynamic state functions, and now you know what thermodynamic state functions are from our earlier lectures. These are functions which depend on the state of the system. They are not path functions, and mathematically they're exact functions, the exact differentials. And we also said that there are other two functions which are not state functions, that's heat and work. They are path functions. Now, another thing which I need to mention at this particular point is the specific volume. Because quite number of people confuse that specific volume. Specific volume is the reciprocal of density. Specific volume is the reciprocal of density. And its units are meter cubed per kilogram. Always remember that. So you have to be very, very careful when you're dealing with volume and when you're dealing with specific volume. Specific volume. So you need to know what you're talking about. Now, the differences between these properties can be expressed if we just use the general term. Generally, the differences between these properties, between the properties which we labeled as X can be expressed as, we can express that as X is equals to Xg minus Xf, and that is equals to Xgf. So that if we have, for example, if we use the practical ones which we have, enthalpy, we can express as Hg minus Hf is equals to Hgf. Internal energy, Ug minus Uf is equals to Uf. Entropy, Sg minus Sf is equals to Sgf. Specific volume, Vg minus Vf is equals to Vgf. Remember, that is gas or vapor, and that is liquid. So we can express these properties generally as that. Now, suppose we say that our point of reference, because remember, when we are talking of enthalpy and internal energy, we have a very good thermodynamic relationship between enthalpy and internal energy, which tells us that H is equals to U plus PV. Suppose we just create a state, just like when we are doing thermochemistry, we say that the enthalpies of the elements is zero. suppose we say that the internal energy is equals to 0 when pressure is P naught V naught. P naught V naught. Therefore, in that case, H will be P naught V naught. That you have put that as a reference state. But in practical reality, it is assumed, pressure temperature diagram, let's have back to water one, that at the triple point here, it's assumed that U is equals to 0 at the triple point. We are always assuming that at the triple point, U is equals to 0 and S is equals to 0. That is, at the triple point, it is assumed that U, the internal energy, is 0 and S, the entropy, is 0. So what does that mean? So if we use that at the triple point, remember that's where the solid, liquid and gas coexist together in equilibrium. Their chemical potentials are the same and so forth. And we had seen it was a reference to the pressure of the triple point and the critical pressure. Now we are saying at the triple point, U is equals to 0, S is equals to 0. Therefore, if we plug that in the expression for enthalpy and internal energy, then we see that H is equals to 0 at the triple point plus, what was the pressure at the triple point? Remember, it was 0.006112 bars, and then times the specific volume at that point is 0.001 meters cubed per kilogram. That is in the steam tables. So if you look at the specific volume for the liquid in the steam table, you are going to see that it's 0.001. We have rounded it off. And you will find out that the specific volume for the liquid does not change significantly with the pressure. So we can always assume it is constant. Because compressing a liquid, compressing a liquid is quite a task. So normally the specific volume for the liquid is relatively constant. So we always can use 0.001 meters cubed per kilogram for our values, even though we value the pressure. So if you go, for example, if you are to say at 20 bars, you find the specific volume for the liquid is the same. At 50 kilopascals, it's still the same, and so forth and so forth. So it's relatively unchanged. Now, so this is at the triple point. U is 0. We have our pressure corresponding to the triple point pressure, and we have our volume at that particular point. So what is important here is just look at the units. So to get sensible units there, relatively rationalized units, we will have 0.006112 bars times 10 to the power 5 newtons per meter squared per bar times 0.001 meter cubed per kilogram times 10 to the power minus 3 kilonewton meters per newton meter. So that you want to get your answers in kilojoules per kilogram, the units of enthalpy. You want to get them in kilojoules per kilogram. So it's very important for you to always do dimension analysis and see that you get the correct values there, which will, when you cancel those dimensions, you should actually end up with, you should end up with kilojoules per kilogram. In other words, you should end up with Newton meter per kilogram, because joules is Newton meter. So joules is Newton meter per kilogram. Very, very important for us to take note of that. So, I repeat, we have the steam tables. That's a very important quantity for you to operate, because it's the one which has the values for saturated pressure, saturation pressure values for steam. It's the one which has saturation temperature values for steam. It's the one which has the superheated vapor values for steam, and has the compressed liquid values for steam. And so once you get one of the properties, you're able to get the rest. Now, when you go to the superheated vapor values, if you look at our lectures, or some of our earlier lectures, we talked about degree of superheat. Degree of superheat. And we say that if you look at the temperature, entropy diagram, temperature entropy diagram, this is the saturation pressure. Remember, that's the saturation pressure. And here we have liquid and gas phase. Liquid, gas. What are we saying? In the superheat region here, we can have the vapor at temperatures higher than its normal boiling point at the saturation pressure. Suppose that difference in temperature, we mark it as that, delta T. Delta T. Let's call it TS. Now, suppose we are talking of steam at saturated vapor at that pressure, at a temperature of 213 Fahrenheit, degrees Fahrenheit, 212 degrees Fahrenheit, the normal boiling. And now it is at 213 degrees Fahrenheit. Remember, the Fahrenheit, in terms of Celsius, the Fahrenheit degree is simply minus 32 times 5/9. That's the conversion of Fahrenheit and the Celsius scales. So if it's at 213 degrees Fahrenheit, the difference here is 1 degree Fahrenheit. So the degree of superheat is 1 degrees Fahrenheit. And that is the superheat region, whose data you are going to find in the superheated vapor tables for steam. And here also we have the compressed liquid region, where we have our compressed liquid region. So we can have cooling in this region here. Just the same way, let's call it that. So we have the cooling in this particular region. And we have discussed that extensively in some of the earlier lectures, where we talked of the degrees of superheat. Very important degrees of superheat and what it means. And we referred to the steam table. So just go back to that lecture. You're going to find more detailed discussion on that. So the superheated vapor table for steam and the compressed liquid table for steam are just corresponding to these regions and corresponding to these regions. And remember, if you look at the pressure volume diagram, if you look at the pressure volume diagram, let us at constant temperature, if you are compressing your system at some temperature T1, constant temperature, you notice when you come to the liquid region, the curve will be quite steep. Because it's very difficult to compress liquid. Here is liquid plus vapor. It's called wet vapor. We have wet vapor where we have a mixture of saturated liquid and saturated vapor. And there we talk about the dryness fraction, which will be in other lectures shortly. So that's very, very important for us to know. So that if you're at another temperature, T2, for example, then again, you will see that it's much steeper. So those are the quantities dealt with in the compressed liquid component of the steam table. So these ones, the superheated region, are the ones dealt with in the superheated vapor table for steam. So we'll stop at this particular point, and we'll pick up the other thermodynamic lectures. Thank you.